Oh, hello everyone, this is Dr. Garrick. Labor Economics Chapter 3, Labor Demand Chapter, Part 4. In this part, we will talk about the relationship between profit maximization and cost minimization. We will also talk about isoquants and isocosts and how they help us to determine the profit maximization issue. So a couple of things. I want you to understand that profit maximization implies cost minimization. That means if you are maximizing your profits, you are at the same time minimizing your costs. However, the reverse is not necessarily true. If you're minimizing your costs, you're not necessarily maximizing your profit. You could be, but only if you were you're producing the best optimal profit maximizing output level. So after this introduction, let's get started. So profit maximization in the long run, we talked about the rules, right? Value marginal product of employment, labor, has to be equal to wage rate, and also value marginal product of capital is going to be equal to the rental rate. So in the long run, actually I got ahead of myself, but this is what we learned from previous parts. This is coming up. Okay, in the long run, the firm maximizes its profits by choosing not only how many workers to hire, but also how much capital to hire. So how many plants, equipments, tools to invest on. So you're choosing both your employment level, number of workers, and capital, okay? So short-term profit maximization, if you remember, we are choosing the best level of workers or optimal labor level to maximize profits, right? Profits in the short run, I don't know why that is happening, but we can just erase it. So pi of E, this is profit function. I'm trying to just write E here in parentheses. Okay, it doesn't want to, right? Is going to be, this is my total revenue, price times quantity. This is production function. So if there's anything here that's confusing, start watching this chapter 3 from part 1. So go to this playlist and go to the top of it, okay? Minus, this is the total cost for the short run, right? Wages times number of people employed, and this problem yielded the optimal level of employment from this equality that came from first order conditions, first derivatives being equal to 0. Long run profit maximization is a little different. You not only choose employment level, but you also choose your capital level. To maximize, now you have the full long run profit function. Your profit function here, this pi, not only depends on employment, but also, depends on capital. Okay? So price times quantity, total revenue, this whole part is total revenue minus total cost of labor and total cost of capital. This R is supposed to be little r. Excuse that mistake, okay? So let's analyze long run profit maximization. Let's do it both mathematically. We did it actually for the short run. And also we will talk about this graphically, all right? So mathematically, we are going to choose both E and K to maximize employment and capital, to maximize this profit function. So you're going to take first derivative. We call these first order conditions in economics and math. First order conditions are first derivative of the production function with respect to E and K. Remember in the previous part when we were taking the first derivative of regular function with production function, that was only a function of employment level, right? Workers, labor. So what we did was we used D for differentiation because we have two variables in this equation now, both E and K, both labor and capital. You need to use, instead of that D, we're going to use this. This is called delta. Again, partial derivative when you have more than one variable. Okay, so this delta, right, it's same thing, fancy way of using delta. This was discrete change, right, 1 unit change. We use D if we had one variable that we are choosing, endogenous variable. And then we're going to use this delta, same thing, because we have more than one variable. We have E and K, okay? Delta pi with respect to delta E, okay? With respect to E, delta E is going to be the same idea, price, but now the partial derivative of this with respect to E. So this is called the partial derivative, because if you have more than one variable, that's called partial derivative of F with respect to E minus, same thing, minus WE, first derivative of anything that has power 1, just disappears, minus W equals 0. Same thing, we do so this is exactly what we had before, right? Price times marginal product of employment, labor. So this means in English, if I increase labor employment by 1 unit, what's going to happen to my quantity output level? We do the same thing with respect to capital. This is an important part. So price times, now we're taking the first derivative of this function, partial derivative with respect to K this time, okay? Minus, this becomes a constant number. This appears when we're taking derivative of profit function with respect to K. And from here we have negative R equals to 0. Rearranging, we get something very similar, right? We talked about this. Price times marginal product of labor is equal to wages. Price times marginal product of capital equals to the rental rate. So again, value marginal product of labor is equal to the wages. And then value marginal product of capital is equal to the rental rate. So what we did here is we just divided these two sides, okay, with each other. So let's divide left hand side with the left hand side of this equality. Let's divide the right hand side of this with this side. So if we do this, excuse me, prices will cancel out. So you get marginal product of labor divided by capital equal to the wage rental rate ratio. Interesting. If you rearrange this, so just swap the locations of this, you can do that. You can move W here. You can move marginal product of capital here. You can just swap that. What you see here is marginal product of labor divided by wage rate equals marginal product of capital divided by the rental rate. Excuse me. I should have inserted some elevator music. But this in English, let me explain it to you what it means in English. This is basically how many quantities of output I am producing by spending $1 to labor. I have $1. If I put that in hiring a labor, this is how many quantities of output I'm going to get. I have another $1. This is how many units of output I'm going to get if I put $1 to capital. So you hire labor capital combination to the point at which the last dollar spent on either one of them brings you the same quantity of output. So choose input such that the last dollar spent on either capital or labor brings in the same amount of additional output. What if we had this? What's wrong with this? Oh no. This means in English, listen to me carefully. This means in English, $1 spent on labor, I'm gonna put a stick person figure, brings more output. So let's say it's producing apples, 1, 2, 3 apples. Okay, so you spend $1 on workers, and that $1 spent on the labor brings 3 apples. Okay, $1 spent on capital. When I have capital, I'm actually going to put a computer. Okay, laptop computer. $1 I spent on keyboard. Laptop computer brings me 2 apples. I just told them made up. So use the logic, right? Interesting. So if I had $1, where should you spend your money? Labor or capital? Of course, labor. Increase employment. Either decrease capital or keep it same if you can. But increase employment, technically if you want to decrease it. And the opposite is true. If this is the case, I'm going to grab a different color, folks, blue. If this is the case, that means capital is bringing you, per dollar spent on capital, you get more output. So you better increase your capital. The last dollar you spend on labor brings you less output. So I need to not employ as many workers. Okay. So we have talked about profit maximization, and let's talk about cost minimization graphically in the long run. Cost minimization example. So we are going to use what we call isoquants. Remember chapter 2? In chapter 2 we did labor supply model, right? In that labor supply model, we were showing indifference curves. Indifference curve showed you, if you remember, labor consumption preference, and we had ISO. These were not isoquants. I was going to say isoquants. These were indifference curves, ICs. They represented level of utility, indifference curves, okay? So I'm going to get rid of that portion. Isoquants are going to be looking somewhat similar to that. Okay, so you can represent output using isoquants. So we put capital on the y-axis. We put labor on the x-axis, employment, workers. So each isoquant will show you level of output, constant level of output we are producing. I don't know, I'm going to make up a number, folks. Let's say this is 500 units of cars, okay? So any of the combinations on this blue line will give you 500 units of output using different combinations. An isoquant shows possible combinations of both employment and capital that would produce the same level of output. So for instance, look at point B. Point B employs fewer capital, more labor, versus point A employs fewer workers, more capital, but they both achieve the same level of Q0 level of output, whatever you're producing. An isoquant shows possible combinations of employment, labor, and capital that would produce the same level of output. A and B points both produce Q0, great. And it doesn't matter which one you use, you're still producing the same level of output. Let's talk about the properties of the isoquants next. They are downward sloping. Look. Number 2, slope of an isoquant will be equal to the marginal product of labor divided by marginal product of capital. Isoquants do not intersect with each other, just like indifference curves. And higher isoquants mean higher level of output. So imagine another isoquant Q1, if this is 500 cars, right? This is going to be, I don't know, 700 cars. Yes? And all these points on this new Q1 shows different combinations of capital and employment that produce the same level of output. This was almost perfect outlining. It's pretty hard. All right. The last property of isoquants is that they are convex to the origin. Convex to the origin. Convex means it's just like the indifference curves. They are like bowl, but the bottom of the bowl, like imagine the cereal bowl. I know you're like, what is she talking about? This is like a cereal bowl, right? The bottom of the bowl is pointing out the origin, okay? They are convex to the origin. This shows diminishing marginal rate of technical substitution. What does it mean? As I am employing more and more labor, I want to be using more and more labor, okay? What happens is that you're hiring more labor, marginal product of labor is going to go down, okay? So the slope of isoquant will become flatter. At the same time, marginal product of capital is going to go up. And both effects will cause slope to get flatter. Okay? So I want you to know that as you keep hiring more and more labor, marginal product of labor after a point is going to go down. This is called diminishing marginal product of labor. We talked about this. This is part 1. Okay, so these are the properties of the isoquants. Okay, so let's talk about the slope of an isoquant. Slope of an isoquant is the negative of marginal product of labor, whatever you have on the x-axis, divided by marginal product of capital. One way to find it is to take total derivative. This is called total differentiation. Total differentiation, if you're interested, I'm happy to point you towards some videos that are online. And it's super easy. Whoever scared you of math, no, don't listen to them. Total differentiation means I'm trying to look at the total change in quantity. And what can change quantity? There are two things that can affect quantity: employment level and capital. Yes? So I'm going to then, this is the rule, take the first derivative of this whole production function with respect to employment, labor, times changing employment. So in English, this means, if I change employment by infinitesimal unit, how will my output change? Marginal product of labor times how much did the employment level change? Isn't this exactly how a change in employment have impact on the quantity? How many units of workers did we see changing? It could be increase, decrease, but let's say how many more workers are we employing and how many do each of these workers bring in? Yes? Yeah. Same idea. You then have the plus sign because there are two variables. Then take the first derivative of this function with respect to k now times change in k. This is marginal product of. This in English, this means if I increase capital by infinitesimal amount or change it, how much will this output change? Marginal product of capital times capital. That's so simple. Changing capital. I apologize. Okay. So by definition, this is the really fun part. By definition, on an isoquant, right? On an isoquant, what does not change? On an isoquant, changing quantity is absolutely zero. I'm always producing 500 units, same quantity. So equalize this whole thing to 0, okay? So this is marginal product of labor times change in labor plus marginal product of capital times change in capital. Throw this one to the other side. It goes to the other side as negative marginal product of employment times change in employment, okay? And then divide everything by delta E. Or we are just manipulating and reorganizing just till we find this guy. change in K over change in E. That is the slope, rise over run. That's the slope of this, right? This segment, rise, change in K over run. I'm actually, you know what I'm going to do, folks? We skipped a step here. I'm going to just show you exactly how those steps happen. Okay, I just feel like I need to, from this, how did we come to this? If you know how to do it, do it. Pause the video and do it. But I'm going to show it to you. So first, let's throw this first item to the other side. Let's start with that. So I have from this side, left-hand side, marginal product of capital times change in capital. So I'm throwing this thing to the right-hand side. Anything positive, switch a sign, going to the other side of the equality, marginal product of labor times change in labor. I want to have delta K divided by delta L, okay? So divide everything by delta L, okay? Delta K over delta L. These will cancel out. Now, on the left-hand side, I also have this guy. I don't want this. I want to divide everything by marginal product of capital then. Divided marginal product of capital. Boom, boom, cancel out. Change in capital divided by change in labor. I keep putting L. I'm going to switch back to E because guess what? We use E for employment, L used for leisure. All right. Okay, so then we have here negative marginal product of labor. It's hard to say labor and put an E. Divide by marginal product of capital. That's the slope of an isoquant. There we go. So marginal product of labor divided by marginal product capital is called the marginal rate of technical substitution. Know that. So the absolute value of the slope of an isoquant is called marginal rate of technical substitution. So let me give you an example. What does it mean? Marginal rate of substitution tells you at what rate should you change your capital to produce the same amount but hire more workers. So how many units of capital do you give up? This is a really cool example. There are two ways to mow a 1,000 square foot lawn. You can, for instance, look at point A. This is like mowing a 1,000 square foot lawn, 1,000 units. Capital labor, we have point A, we'll also have point B. Point A uses fewer workers, so it uses 2 workers. You are using 42-inch mowers, 42 inches. This is a bigger capital, okay? So you have 2 workers using 42-inch mowers versus more capital intensive, versus you have 4 workers, point B, and only 21-inch mower. I'm talking about like the machines we cut the grass, right? Some of them are smaller, some of them are really big. So I'm talking about the bigger ones. Let's talk about, now we put isocosts together. Let's talk about isoquants together. My brain is moving forward. Let's talk about isocost lines. Thank you. Isocost lines show various combinations of employment, labor, and capital that are equally costly. They are just like budget lines. So you're probably having like deja vu. Yes, it's very similar because it's like budget lines. So imagine total cost, right? Total cost is going to be equal to, right, wage rate times number of workers plus rental rate, this is the price of capital, times number of capital. So if you want to draw this, pick a level of cost. I put C0. This could be 100. I don't know. Let's look at extreme points, okay? So if if K is 0, that means I am only hiring labor. This thing will disappear. So you have C0 equals WE. That means you can actually C0 divided by W. Okay. So you have this level of labor you can hire the most. Let me give you an example. I'm just going to give you a number. Okay, so imagine total cost $100. Wage rate is $10. Rental rate is $20. Okay. So if you have $100 to spend, wage rate is $10, I can hire 10 people. So this C0 divided by W is going to be 10. Okay. So if on the other hand, let's pick a different color, and I need to erase it a little bit. Let's clean it up. Let's look at the other case. What if we hired, I'm trying to find this point now. What if we hired only capital? So what if the other extreme, I am not hiring any workers. This is 0. So you would get C0 equal to RK. Divide everything by R. Okay. Okay, so you have maximum level of capital you can hire is total cost divided by R. So if total cost is 100 divided by 20, you're going to get 5 maximum number of workers you can capital you can hire. So what is the slope of this line? This is going to be, how do you find it? This is downward sloping, so I'm going to put negative. I'm just using the simplest rule, negative rise over run. Do you remember? It doesn't always work, but in this case, it's going to work. Rise over run. Negative, what's the rise? This distance. Negative 5 over run is this horizontal distance 10. So it's going to be 5 over 10 negative 0.5. Another way to find the slope is going to be negative general formula. I'm talking about general formula, negative W over R. Yes? So negative 10 over 20, 0.5, or negative 1 over 2. Okay? So what did we learn? We learned to determine this intercepts. Okay? Slope here, it's let me clear everything. Slope is negative W over R. Okay? So what happens if the cost goes up? Higher isocost curve means higher cost levels. Higher isocost lines indicate higher costs. So here, so C1 is greater than C0. It's a parallel shift. That means cost has gone up. Higher isocosts will lie to the right hand side of the original isocost curve. So cost minimization. This is the fun part. It's very easy. We are trying to find the optimal level of capital and labor that would minimize my costs. Okay. So I don't know. I want to produce Q0. I don't know if this Q0 is the best level of output. Is this profit maximizing? I don't know. But if this Q0 is profit maximizing level, and if you're minimizing cost at the same time, then that becomes the best level of output and you're doing it right. But imagine I want to produce Q0. I don't know if this is the best level. We'll talk about that. It's coming up. So I'm trying to do it at the best, lowest cost possible. It's available in calculus, but again, you're not responsible with this calculus. I just want you to know how to do these things graphically, okay? So capital is here, employment is here, okay? So I have this I have my isoquant. I'm trying to find the lowest iso cost curve. Look, I have isocost C0, this one, and I have this one. So I'm trying to find the lowest, the one that's closest to the origin. You can produce these level of output. I don't know, let this be 500 units of cars, okay? So a firm minimizes the cost of producing Q0 units of output by using capital labor combination at point P. So this is the best. I'm going to put K star. So this is cost minimization and E star, best level. Anything that is not all at this point, because I'm at the lowest. I would like to produce at a lower cost, but with this cost curve, I can't reach it to my production goal of 500, this black isoquant curve, right? Why wouldn't I pick any point such as A or B? First of all, look at point A. It lies on a higher cost curve. Don't go there, it's too high. Point B also lies on this higher cost curve. All other combinations, A and B, lie on the higher isocost. Plus, I want to talk about point A. At point A, we have something little bit disturbing, okay? So, slope of this budget line, absolute value. Look at this. It is flatter than the slope of the isoquant right here. I'm going to draw it better. I can do better. So at point A, this is the slope of the isocost curve, which is negative W over R, okay? In absolute value, this is actually flatter than this guy's slope at this point. So slope of this isoquant Q0, I'm marking it with a highlighter. So slope of this isoquant curve Q0 at, let's say, point A is going to be super steep, right? This is then greater than negative of marginal absolute value of negative of marginal product of labor divided by marginal product of capital. Absolute value gets rid of negative signs. W over R less than marginal product of labor, marginal product of capital. You can actually move these, okay? So let's put wages here, marginal product of capital up there. So I'm just going to swap them. So you move this to the numerator left hand side, top part left hand side, marginal product of capital divided by rental rate less than marginal product of labor divided by, I'm swapping the W down here. Do you know what this means? $1 spent on labor brings me much more higher level of output. Therefore, I need to be hiring more. I need to get rid of some capital because every dollar spent on labor brings me more output. Guess what? How can it be optimal? Optimal best combination means there's no other level, there's no other combination that gives me the lowest cost. Guess what? By increasing employment at point A, I can actually simply lower the cost. Here, you are already at your best level of output. So at point P, the isoquant is tangent to the isocost. Slope of the isoquant is exactly equal to slope of isocost. So at this point P, I'm going back to point P. Negative of marginal product of labor divided by marginal product of capital is exactly equal to the wage over negative of wage over rental rate. If you clean this up, you're gonna get marginal product of labor divided by wage rate equals to the marginal product of capital divided by rental rate, which means every dollar spent on either labor or capital brings me exactly the same level of output. Okay, so let's wrap it up. Cost minimization. Cost minimization is very important. My brain is just racing. Okay, so I need to calm down. Cost minimization is very important, but it doesn't always imply profit maximization. Profit maximization always means cost is being minimized too. But cost minimization doesn't necessarily imply profit maximization. Cost minimization says a firm will choose the least cost combination of capital and labor, but the least cost choice is where the isocost line is tangent to the isoquant. Okay? However, is this isoquant representing the best level of profit maximizing level? As a result, cost minimization gives you margin rate of substitution equals to the ratio of input prices at the least cost choice. Cost minimization to produce Q0 is a necessary condition for profit maximization, but not sufficient because we are trying to produce Q0 at the lowest cost. Is this Q0 Q star, meaning is it profit maximizing level? So profit maximizing doesn't choose any level of Q. It chooses Q star, which means that's the best level of output. Okay, next part is really important. We are going to put everything together in the next part. So for sure, don't stop watching it here. Go to the next part and I'll catch you there. Don't forget to subscribe, folks, because that is how you will learn about new uploaded videos, number one. Number two, also let me know what other courses you want to see here, what videos you want me to make.